We will now discuss some specific 2D sampling techniques which you will need in practice to implement your Monte Carlo path tracer. These techniques are important in order to do basic things like sampling the hemisphere or sampling the BRDF. It is the final step in tracing the reflected ray. You have to pick an actual 2D direction. For example, according to the projected solid angle or the BRDF or the area on the light source, or perhaps even sampling a triangle on geometry. The first sampling method we will discuss is to uniformly sample the upper hemisphere. So this is uniform directional sample. How do you generate a random ray on the hemisphere? The first option is rejection sampling. So you generate random numbers x, y, and z with x, y, and z in -1 to +1. That is, x, y, and z are in the cube with range from -1 to +1. If x squared plus y squared plus z squared is greater than 1, that is, the point lies outside the sphere, then you reject it. A similar kind of idea can be used for sampling a circle in 2D. Drawing this in 2D for simplicity, let's say you have a square like this, -1 to +1, and you want to sample the circle inside the square. So if you pick a point here, this point will be reject. But if you pick a point here, this point will be accepted. Similar idea for a sphere. Moreover, for the hemisphere, if the point lies below the horizon, if the dot product with the normal is less than 0, then you simply flip x, y, and z, you negate them. And of course, you normalize x, y, and z before doing this. So you take x, y, and z and you divide by the square root of x squared plus y squared plus z squared. This gives you a random direction on the visible hemisphere. Since that occupies 2 pi steradians, the probability is 1 over 2 pi, and the estimator needs to be multiplied by 2 pi. A second option for sampling the hemisphere is an inversion method. Remember that the integral of solid angle is sine theta d theta d phi. So d omega is given by sine theta d theta d phi. Or you can think about this, if you remember your calculus, as d of cos theta times d phi, which means effectively you need to sample according to z or cos theta. And then you can invert the cumulative distribution function. The recipe for how this works is as follows. You generate phi in 0 to 2 pi. That is, you just take your uniform random number generator that goes between 0 and 1, and you multiply that by 2 pi. Then you generate z, which corresponds to cos theta in 0 to 1, since it's the upper or the visible hemisphere. And you simply let theta is equal to the inverse cosine of z. Z is just your uniform random variable. Now you can let the x, y, and z coordinates that you want be sine theta cos phi, sine theta sine phi, and cos theta, which are simply the spherical coordinates theta and phi expressed in terms of Cartesian coordinates. Finally, we'll discuss this in the next lecture. You may need to apply a rotation to align the z direction with the surface normal. For homework 3, this is all you need to do. Simple upper hemisphere sampling. I have described 2 methods. One is rejection sampling, and one is based on inverting the CDF and the actual inversion method. Anything more advanced you do, such as importance sampling that we'll talk about in a moment, is extra for homework 3, but parts of it will be required in homework 4. So instead of choosing a direction randomly on the hemisphere, a better idea is to do importance sampling according to the BRDF. Notice that in the reflection equation or the rendering equation, you multiply by the BRDF times the cosine of the incident direction. So ideally, you should importance sample according to this light transport operator corresponding to the BRDF times the cosine. One example of that is cosine weighted Lambertian sampling, which effectively corresponds to the projected solid angle. The density in this case is cos theta times the solid angle, which will be sine theta d theta d phi. And you can work out that in this case, the integral of that is cos theta d cos theta, so it's proportional to cosine square theta. And if you want to invert it, instead of just doing cosine inverse, you have to take cosine inverse of the square root. So the recipe is simply generate phi in 0 to 2 pi, take your uniform random number generator between 0 and 1, multiply by 2 pi, then generate z in 0 and 1, that's again your uniform random number generator, but then theta is equal to cos inverse square root of z. Another example, Phong BRDFs, which you will be considering in your assignment, where the BRDF is proportional to cosine power n alpha, where alpha is the angle between the outgoing ray and the ideal mirror direction. Notice that in your homework assignments there is a scale factor in order to get things to normalize correctly, so which is ks into n plus 2 divided by 2 pi. It's very difficult to sample this times cosine theta n, so we will just sample the Phong component and then multiply the result by cosine theta n. That is okay. It is still better than purely random sampling. Remember that importance sampling doesn't need to be exact, it just needs to capture the main features of the function you're sampling. So here is the recipe for generating the specular term. You again generate your z value in 0 to 1, but because it's now cosine power n, instead of taking z power 1/2 like you did in the Lambertian case, you take z power 1 over n plus 1, where n can be arbitrary is the Phong shininess. You similarly generate phi alpha in 0 to 2 pi times your uniform random number generator. This gives the direction with respect to the ideal mirror direction. You convert to the Cartesian components x, y, and z, and then you have to apply a rotation so that z corresponds to the mirror direction. The exact specifics of this rotation will be discussed in the next lecture. In summary, Monte Carlo methods are robust and simple, at least until you start working through the nitty-gritty details of how do I do this 2D sampling exactly correctly. For this reason, they are the method of choice for global illumination and what we study in CSE 168. They must handle many variance reduction methods in practice. You can implement a very vanilla path tracer, which is typically used as the base case in papers, and then you argue that your various variance reduction methods leave the problem unbiased but can speed up rendering so much. There are a number of other techniques which we won't go into detail too much, things like bidirectional path tracing, but we have discussed the basics of importance sampling and Russian roulette. This is a rich field with many papers going back to the 1990s, but even in the past 10 years and continuing until today, you have multiple papers at SIGGRAPH each year which are finding new methods for importance sampling.